Time might not be a one-way street after all. We are taught that time flows like a river from the past into the future, a journey that can never be reversed. But hidden within the laws of physics are startling clues that this river could, in theory, flow backwards, yet it never seems to. This video uncovers 21 astonishing clues that time might be reversible, but only in one specific direction. By the end, you will see the universe in a completely new light, understanding why our past is fixed and our future is open. We will explore why a shattered cup never reassembles itself and what the fate of antimatter tells us about the arrow of time. How does your own memory fit into this cosmic puzzle? That cooling cup of coffee is more than just a morning routine. It is a direct window into the deepest laws of the cosmos. We watch heat dissipate into the air, an irreversible process that defines our daily experience of time. This is the thermodynamic arrow of time, our first and most powerful clue. The law behind it, the second law of thermodynamics, states that in any isolated system, entropy, which is a measure of disorder, always increases. Things move from order to chaos, from concentrated energy to dispersed energy. The cream mixes into the coffee, it never unmixes. A scattered deck of cards stays scattered. It does not leap back into a neat, ordered stack. The underlying equations of physics, however, show no preference for past or future. They are perfectly symmetrical. If you were to watch a film of two billiard balls colliding, you could not tell if the film was running forward or backward. The physics would look correct either way. So why does the universe as a whole only run in one direction? The answer seems to lie not in the laws themselves, but in the starting gun. Our universe began in a state of incredibly low entropy, a phenomenally ordered and dense state at the moment of the Big Bang. Like winding up a clockwork toy, that initial condition gave the cosmos a one-way ticket, a direction to evolve toward ever greater disorder. This foundational push from order to chaos is the riverbed down which all other arrows of time flow, including one that operates on a scale so small it defies everyday logic. Yet this riverbed of increasing disorder carved by the Big Bang is not the only channel guiding time's flow. Another clue emerges from a realm where logic itself seems to bend, the quantum world. Here, the rules are different. A single particle is not confined to one location, one state of being. Instead, it exists in a ghostly haze of all possible locations at once, a condition physicists call a superposition. It is both here and there, a blur of potential waiting to be resolved. This strange state persists until the moment the particle is observed or measured. In that instant, the haze vanishes. The infinite possibilities collapse into a single, definite reality. The particle is now firmly here or firmly there. This event, the quantum measurement, is a one-way street. Once the collapse happens, it does not reverse. The particle does not spontaneously decide to return to its fuzzy, unobserved state of pure potential. This irreversible collapse creates a quantum arrow of time. The perplexing part is that the equations describing the particle's behavior before the measurement are perfectly symmetrical. They work just as well running backwards as forwards. It is the act of measurement itself that introduces the irreversible step. This forces a profound question. Does the very act of observing the universe, perhaps even consciousness itself, play a role in cementing time's forward direction? Is our attention the hammer that nails reality into place? This intimate link between observation and reality hints at an even more personal arrow of time, one that is woven into the fabric of our own minds. This intimate link between our minds and reality finds a startling echo in the behavior of the universe's most fundamental building blocks. The third clue comes from a cosmic near miss, a moment in the first second of existence when everything almost cancelled out into nothing. After the Big Bang, the universe should have created perfect, equal amounts of matter and antimatter. Think of them as cosmic opposites, destined to annihilate on contact in a flash of energy. If that initial balance had held, every particle of matter would have met its antimatter twin, and the entire cosmos would have vanished in a brilliant final fireworks show, leaving behind an empty sea of light. We are here, which means that perfect symmetry was broken. Something tipped the scales ever so slightly in favor of matter. For every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny surplus, the 1 in a billion that survived the annihilation, is what all the stars, planets, and we ourselves are made from. This bias is known as CP violation, a subtle but profound crack in the mirror of nature. It means the laws of physics treat particles and their mirror image antiparticles slightly differently. This is where the arrow of time enters the picture. Through a deep principle of physics called the CPT theorem, a violation of CP symmetry necessarily implies a violation of T symmetry, time reversal. The universe's preference for matter over antimatter is direct evidence that the laws of physics themselves are not perfectly symmetric when time is run backwards. The microscopic rules of the game have a built-in arrow, a fundamental preference for one direction of time over the other. This particle-level bias, discovered in the heart of atom smashers, connects directly to the grandest scale imaginable, the expansion of the universe itself. That fundamental bias in the laws of physics, favoring matter over antimatter, set the stage for the entire cosmic story that followed. And the setting for that story is an arena that is constantly growing. The fourth clue to time's one-way direction is written across the sky itself, in the motion of every distant galaxy. In the 1920s, an astronomer named Edwin Hubble made a staggering observation. By analyzing the light from far-off galaxies, he found that they were all rushing away from us. More remarkably, the farther away a galaxy was, the faster it appeared to be receding. The entire universe, the very fabric of space, was stretching like the surface of an inflating balloon. This discovery of cosmic expansion defined a new arrow of time, a cosmological arrow. The universe was smaller, hotter, and denser in the past, and it is becoming larger, colder, and more diffuse in the future. We can point to a past moment of incredible density, the Big Bang, but we cannot point to a future moment of similar compression. This gives the cosmos a clear before and after. This leads to a fascinating thought experiment. If the universe's expansion were to slow, stop, and reverse into a great contraction, a big crunch, would time itself run backwards? Would broken cups reassemble and people grow younger? Most physicists believe the answer is no. The relentless increase of entropy, of disorder, would likely continue its climb even as the universe collapsed. The arrow of time, set in motion by that initial low entropy state, seems to be a one-way street with no U-turns. The expansion of the universe, then, might not be the direct cause of time's arrow. Instead, it provides the perfect conditions for that arrow to manifest. The relentless stretching of space creates an ever larger arena, an ever-growing number of possible arrangements for particles, which allows entropy to increase without limit. It is the stage upon which the irreversible play of history can unfold. This grand stage, however, forces us to confront the ultimate question: where did the stage itself come from? What was the initial condition that gave time its direction in the first place? That initial condition of near-perfect order is the fifth and perhaps most profound clue. The Big Bang was not a chaotic explosion in the way we normally think of one. It was a state of extraordinarily low entropy, an immensely ordered and compact configuration. Imagine the most organized library imaginable, with every single book perfectly aligned and sorted. Now imagine that entire library compressed into a single, infinitesimal point. That is the kind of impossible order the universe was born with. This unique starting point is like winding up a clockwork toy. It gives the universe somewhere to go, providing the steep gradient down which entropy can and must increase for billions of years. Why was the initial state so ordered? This remains one of cosmology's biggest mysteries, a question that sits at the very edge of our understanding. Some theories suggest this low entropy state was a statistical fluke, a one in an unimaginably vast number chance that set everything in motion. Its existence is the ultimate reason we remember the past and not the future, because the past is the state of lower entropy from which we have flowed. This initial condition, this single wound-up spring at the beginning of everything, forces us to look toward the universe's possible end. If time's arrow is tied to the dispersal of energy from a state of low entropy, what happens when there is no more energy left to disperse? This leads us to a haunting and seemingly final vision for the far, far future, a state known as the heat death of the universe. This ultimate state of maximum entropy, the heat death, is our sixth clue. It paints a picture of a universe that has simply run out of steam. Billions of years from now, all stars will have burned out, their fuel exhausted. Black holes will have evaporated through a slow trickle of radiation. Matter itself will have decayed into its most stable, inert forms. The cosmos will be a thin, lukewarm soup of particles, spread so evenly across an unimaginably vast space that no heat can flow from a hotter place to a colder one, because everywhere will be the same frigid temperature. In this final equilibrium, no more work can be done, no engines can run, no life can exist, and no events of any significance can occur. In such a universe, the very concept of time loses its meaning. With no processes to mark its passage, with no change from one moment to the next, the arrow of time simply vanishes. There is no before or after, only a perpetual, featureless now. But what if the universe takes a different path? What if the expansion slows and reverses, leading to a big crunch where all matter and energy collapse back into a singularity? Surely you might think time would run in reverse. We would see shattered galaxies reassemble and stars ignite from clouds of cold dust. Yet most physicists argue this is an illusion. Even as the universe collapses, the thermodynamic processes within it would not reverse. The fundamental rule that disorder increases would still hold sway. A burned log would not unburn during the collapse. The scattered ashes of a star would not spontaneously gather back into a fiery sphere. The asymmetry is locked in. The universe had a very specific low-entropy beginning, a singular starting gun. Its end, whether a cold fade or a fiery crunch, is a state of incredibly high entropy. This stark difference between the start and the finish, regardless of the final fate, reinforces that time's journey is a one-way trip. It is this irreversible flow that gives meaning to a concept even more fundamental than energy, the concept of information itself. The irreversible loss of information is a silent, constant process happening all around us. When a log burns in a fireplace, the intricate structure of the wood, a complex record of its growth, is transformed into anonymous ash and heat. The specific information about that unique tree is scrambled into a formless, random state. This is deeply connected to entropy. An increase in disorder is fundamentally an increase in ignorance, a loss of the specific knowledge needed to reconstruct the original ordered state. We can effortlessly turn a meaningful sentence into a random string of letters by shuffling the keys on a keyboard. but reversing the process, unscrambling that chaos back into the sentence, requires immense effort and information. This practical irreversibility of information processing is our seventh clue. It defines a computational arrow of time. Our computers, and indeed our own brains, can easily take a clear input like a memory and process it into a forgotten or corrupted state. But they cannot take that random noise and effortlessly reconstruct the original memory. This one-way street for information is what allows us to have a past that is fixed and a future that is open to computation and choice. Yet, quantum mechanics presents a profound puzzle here. The fundamental laws suggest that information, like energy, can never be truly destroyed, only hidden. This leads to the black hole information paradox. When an object falls into a black hole, it vanishes from our universe, seemingly erasing all information about it forever. This would violate a core quantum principle. Most physicists now believe the information is not lost but is somehow preserved on the black hole's event horizon, encoded in unimaginably complex ways. However, retrieving it from that scrambled state is so impossibly difficult that for all practical purposes, the information is gone. This paradox highlights the stark difference between theoretical reversibility and practical irreversibility. The universe's laws might, in principle, allow information to be recovered, but the path to doing so is so convoluted that it defines a powerful, one-way arrow of time in our reality. The extreme physics of black holes, where space and time are warped beyond recognition, forces us to consider if time's arrow could ever be bent or broken in such an environment. This paradox pushes at the very limits of our understanding. Black holes, the ultimate symbols of gravitational collapse, might also hold the key to understanding time's stubborn one-way direction. The eighth clue comes from the thermodynamics of these cosmic monsters. At first glance, a black hole seems to be the ultimate eraser of information and order, a place where entropy goes to die. But a profound insight changed that view forever. We learned that black holes themselves possess entropy, a tremendous amount of it. A black hole's entropy is not proportional to its volume, as you might expect, but to the surface area of its event horizon, the point of no return. This means the larger the black hole, the more disordered it is. When anything, from a stray asteroid to an entire star, falls through the event horizon, the black hole's surface area increases. Its entropy grows. This process perfectly obeys the second law of thermodynamics. The total entropy of the universe, now including the black hole's immense contribution, always increases. Even these gravitational singularities bow to the arrow of time. Then Stephen Hawking made an even more startling discovery. He realized that black holes are not completely black. Due to weird quantum effects near the event horizon, they slowly radiate energy like a faint steam rising from a dark pond. This Hawking radiation causes the black hole to lose mass over astronomical timescales, eventually evaporating completely. But this creates an enormous problem, the black hole information paradox. All the information about the matter that fell into the black hole, the specific arrangement of atoms that made up a star or a person, seems to be permanently lost when the black hole vanishes. This violates a sacred principle of quantum mechanics, which states that information can never be truly destroyed. It can be scrambled, hidden, or made incredibly difficult to retrieve, but it must, in principle, be recoverable. The evaporation of a black hole suggests a fundamental conflict between our theory of gravity, general relativity, and our theory of the small, quantum mechanics. Resolving this paradox may force us to accept that time's irreversibility is baked into the fabric of spacetime itself, that information loss is a real and final process. This gravitational clue from the largest objects in the universe finds a bizarre and beautiful mirror in the world of the impossibly small. This subtle bias in the laws of physics is not just a grand cosmic principle, it has been caught in the act within the heart of individual particles. Our ninth clue comes from the fleeting existence of a subatomic particle called the neutral kaon. Kaons are strange and ghostly entities produced in high-energy collisions, and they live for only a minuscule fraction of a second. During their brief lives, they perform a remarkable dance. A neutral kaon can spontaneously transform into its own antiparticle, the antikaon, and then oscillate back again. If the laws of physics were perfectly symmetric in time, this oscillation would be a perfectly balanced seesaw. The rate at which a kaon decays into other particles should be exactly the same as the rate for an antikaon. But incredibly, it is not. Painstakingly precise experiments have measured a tiny but undeniable difference. Kaons and antikaons decay at slightly different rates. This is a direct observation of T-violation, a crack in the mirror of time itself at the most fundamental level. It is not a theoretical idea, it is a measured fact. The universe, in its most basic building blocks, treats the forward and backward directions of time as distinct. While the effect is small, its implications are monumental. It proves that the arrow of time is not an emergent property arising from large-scale statistics, like the scattering of molecules in your coffee cup. It is woven into the very fabric of quantum reality. This microscopic asymmetry, measured in particle accelerators, is a direct thread leading upwards to our own conscious experience. From the quantum dance of a single particle, we now scale up to the vast, intricate landscape of human perception. This intimate connection between cosmic principles and our own minds is perhaps the most personal clue of all. We remember the past, not the future. This psychological arrow of time feels as fundamental as our own existence. Our stream of consciousness flows in one direction, a continuous narrative from memory to anticipation. This is not a mere illusion. It is a direct consequence of the physical world. Your brain is a complex biological machine, a system of neurons firing, chemicals reacting, and electrical signals traveling. Each of these processes is governed by the same thermodynamic laws that govern your cooling coffee. When you form a new memory, your brain undergoes a physical change, a strengthening of neural connections that requires energy and increases local entropy. That memory is then a record of a past state of the universe, a state of lower entropy than the present. You cannot remember the future because the future has not yet left its thermodynamic imprint on your neural circuitry. The very act of recording information, whether on a hard drive or in the folds of your brain, is an irreversible thermodynamic process. This link extends to all of biology. We are born, we grow, we age. A broken bone heals, but the process leaves a scar, a permanent marker of the injury. A species evolves over millions of years, adapting to its environment in a sequence of changes that cannot be rewound. A species that goes extinct does not reappear. An egg, once scrambled, can never be unscrambled back into its shell. These biological processes are arrows pointing steadfastly from past to future, all riding the relentless current of increasing disorder initiated at the Big Bang. Yet, just when we think we have a complete picture, a strange phenomenon from the quantum world challenges this seemingly straightforward connection between our perception and physics. This strange disconnect between our forward-flowing perception and quantum possibilities brings us to the 11th clue, a phenomenon so bizarre it troubled even Einstein. Quantum entanglement links the fates of two particles in an intimate dance that defies common sense. Imagine creating a pair of electrons so deeply connected that their properties are perfectly correlated. You could separate them, sending one to the far side of the galaxy. If you then measure the spin of the electron here on Earth, finding it pointing up, you instantly know its distant twin is pointing down. The information about the state seems to travel between them faster than the speed of light, a ghostly influence that Einstein famously dismissed as spooky action at a distance. This instantaneous connection does not, however, allow us to send a message back in time. The outcome of your measurement here is random. You cannot force the particle to be up or down to transmit a signal. The correlation only becomes apparent after the fact when the results from both particles are compared. So while entanglement challenges our classical understanding of locality, the idea that objects can only be influenced by their immediate surroundings, it does not break the chain of cause and effect as we experience it. The measurement event here still causes the knowledge of the state there, preserving the forward flow of time. Yet some interpretations of quantum mechanics push even this boundary. The idea of retrocausality suggests that the measurement we make now could somehow influence the past state of the particles at the moment they became entangled. It is as if the effect reaches backwards in time to ensure the correlation is set up correctly. Even in this mind-bending scenario, the sequence of events we observe, the cause and effect we record in our notebooks, remains stubbornly consistent with a one-way street. The universe maintains a consistent history from our perspective. This preservation of a stable timeline, even in the face of such profound weirdness, forces us to confront the ultimate question about the nature of the reality we perceive. Einstein's theory of relativity fused time and space into a single, four-dimensional fabric, a concept that challenges our deepest intuitions. If we take this idea to its logical conclusion, we arrive at the block universe. In this view, the past, present, and future are not successive moments but fixed locations, much like points on a map. All of time exists eternally, a vast, unchanging block where your birth, your life, and every event yet to come are already inscribed. The flowing river of time in this picture is a powerful illusion generated by our conscious journey through this static landscape. Yet, even within this timeless block, a profound order is preserved. Space-time is not a formless block. It possesses a rigid structure defined by light cones. Imagine every event in history, every flash of light, as a point in this four-dimensional block. From that point, a future light cone expands outward at the speed of light, defining all points in space-time that the event can possibly influence. Similarly, a past light cone reaches backward, containing all events that could have influenced it. This structure is absolute. No event, no signal, no influence can travel outside its light cone. This means that within the block universe, cause and effect are not illusions. A cause must always lie within the past light cone of its effect. You can never have an event that influences its own past. The block universe, for all its timelessness, has a built-in arrow of causality, a one-way street etched into the geometry of reality itself. This cosmic scaffolding, however, is not perfectly rigid. At the smallest scales, the smooth fabric of space-time is perturbed by quantum uncertainty. The precise locations and energies of particles become fuzzy, introducing a fundamental randomness. This quantum jitter does not break the light cone structure, but it does mean that the future is not deterministically set in stone within the block. The block may contain all possible outcomes, with specific paths only resolving as the universe unfolds. This introduces a fascinating tension between a seemingly fixed reality and an open, probabilistic future, a paradox that brings us to the very edge of what we can comprehend. This strange tension between a fixed past and an open future finds a bizarre echo in a quantum effect that seems to defy time's flow entirely. The 13th clue, the quantum Zeno effect, suggests we can seemingly freeze a moment. Imagine a radioactive atom, a tiny quantum clock ticking down toward its inevitable decay. According to the rules of quantum mechanics, this atom exists in a superposition, a blur of both decayed and not decayed states. Its fate is a matter of probability, not certainty. Now imagine observing this atom, not just once but continuously with a rapid, unblinking stare. Each observation forces the atom's fuzzy state to collapse, to choose a definite reality. If you observe it fast enough, you catch it again and again in its undecayed state. The constant measurement resets the probability clock, effectively preventing the atom from ever making the leap to decay. It is like repeatedly asking a shy performer if they are ready to go on stage. Your very questioning keeps them frozen in the wings, never actually performing. In a very real sense, for that single atom, time appears to stand still. This is the quantum Zeno effect, a name inspired by an ancient Greek philosopher who argued that a flying arrow is motionless because at any single instant it occupies one fixed point in space. But this local freezing of time comes at a profound cost. The act of observation is not a passive, magical event. To measure the atom, you must interact with it. You must shine a photon on it or use some other probe to determine its state. This interaction requires energy. It generates heat. It increases the entropy of the larger system that includes the observer and the measuring device. So, while we can seemingly suspend the arrow of time for one tiny quantum system, we do so by vigorously pushing that arrow forward in the world around it. We create a small island of apparent reversibility or stillness, but only by creating a much larger sea of irreversibility. This is a fundamental trade-off. It is reminiscent of the dream of a perpetual motion machine, a device that could run forever without an energy input. The laws of thermodynamics tell us this is impossible because such a machine would require a local decrease in entropy without any corresponding increase elsewhere, violating the one-way street of the universe. The quantum Zeno effect shows us that even when we find a clever loophole, a way to seemingly halt a process, the overall direction of time is ruthlessly enforced. This delicate trade-off between a quantum object and its environment hints at an even deeper connection, one that may ultimately explain why we perceive a continuous and consistent flow of time at all. That delicate trade-off in the quantum Zeno effect reveals a universal rule, a principle so absolute it has crushed countless dreams of inventors. The 14th clue to time's one-way direction is the absolute impossibility of a perpetual motion machine. For centuries, visionaries have sketched designs for devices that could run forever, powering themselves without any need for fuel. These dreams are not just impractical, they are fundamentally forbidden by the laws of the universe. The most seductive of these is the perpetual motion machine of the second kind. It does not try to create energy from nothing, which is an obvious violation. Instead, it aims to be perfectly efficient. Imagine a ship's engine that draws all the heat it needs from the vast, lukewarm water of the ocean itself. It would convert that disordered thermal energy directly into the orderly motion of the ship's propeller, leaving the ocean slightly cooler. It sounds miraculous, but it is an utter impossibility. Why? Because it would cause a net decrease in entropy. The engine would be taking the random, jiggling motion of countless water molecules and channeling it into a single, unified, useful direction. This is like expecting a scattered deck of cards to spontaneously leap into a perfect, ordered stack all by itself. The universe does not allow such a reversal of disorder. For any real process to occur, some energy must always be wasted as heat, dissipated into the environment and increasing the overall chaos. This waste is not a design flaw, it is a fundamental signature of time's arrow. The relentless need to increase entropy is the reason your car engine gets hot. your computer needs a fan, and why no machine can ever be 100% efficient. This thermodynamic friction is the tax we pay for the forward march of time itself. This principle finds a beautiful and profound expression in the very nature of light, a phenomenon that seems to define the ultimate speed limit of causality. Light itself seems to carry a built-in arrow of time. When you switch on a lamp, light radiates outward from the bulb, spreading through the room. It travels at the ultimate speed, the speed of causality, and it always moves away from its source into the future. This everyday experience is our 15th clue, rooted in the classical laws of electromagnetism. The equations that describe this process offer a solution called the retarded potential. It is a straightforward idea. An electron jiggles in a radio tower, and that disturbance creates an electromagnetic wave that propagates outward, reaching your car radio antenna a fraction of a second later. The cause, the jiggling electron, always comes before the effect, the signal received by your radio. This is the only scenario we ever observe. Yet, the mathematics of electromagnetism is perfectly symmetrical in time. The equations also permit another, deeply strange solution, the advanced potential. This would be a wave that converges from the future onto the electron, arriving at the exact moment it causes the electron to jiggle. It is an effect that precedes its own cause, a ripple moving backwards in time. We never see this. The universe, for reasons not contained within the equations themselves, consistently chooses the retarded solution. It rejects the advanced potential as unphysical. This empirical preference is a powerful enforcement of causal order. Causes must come before effects. This choice is not arbitrary. It is deeply intertwined with the other arrows of time. The outgoing retarded waves carry energy away from their source, dispersing it into the universe and increasing entropy. Incoming advanced waves, by contrast, would bring energy from the vastness of space to a single point, a spontaneous decrease in disorder that the second law of thermodynamics simply forbids. The universe's preference for retarded potentials is a reflection of its overall trend from a low entropy past to a high entropy future. It is the universe ensuring that every link in the chain of cause and effect points in the same direction, fortifying the one-way street of time. The relentless formation of cosmic structure is a story written in gravity. Our 16th clue reveals how the universe evolved from a nearly featureless sea of energy into the intricate web we see today. The Big Bang did not produce galaxies and stars immediately. For hundreds of thousands of years, the infant universe was a hot, dense, and incredibly smooth plasma, like a perfectly blended soup. But there were tiny, random fluctuations, seeds of imperfection so slight they might have been mere quantum whispers. Gravity seized upon these minute variations. Over billions of years, it patiently pulled matter together. Regions that were slightly denser attracted more matter, growing denser still, while emptier regions were left behind. This gravitational snowball effect is profoundly irreversible. A fully formed spiral galaxy, with its billions of stars orbiting a central black hole, represents an astronomical level of order and complexity. It cannot simply unravel. For a galaxy to dissolve back into a smooth, primordial gas cloud, it would have to somehow reverse the relentless pull of gravity and decrease its own immense entropy, a feat the second law of thermodynamics forbids. This growth of structure gives the cosmos a clear historical sequence. We can point to a past where structure was minimal and a present where it is rich and complex. We are living in the golden age of cosmic construction, a fleeting era between the smooth beginning and the eventual dispersal of the heat death. This large-scale structuring is governed by gravity, a force with a unique and puzzling relationship with time. Unlike other fundamental forces, gravity always attracts, never repels. This one-way pull seems to naturally encourage the clumping that defines time's arrow on the grandest scale. Yet, this very force may also hold the key to the most extreme possibility for manipulating time's flow. This fundamental asymmetry in gravity, its unwavering pull, is one of the universe's most powerful engines for creating irreversible change. Gravity is always and only attractive. We have never discovered a negative mass that would be repelled by or repel ordinary matter. This is a profound one-way street built into the fabric of space-time itself. Think of the other fundamental forces. Electromagnetism can be both attractive and repulsive, with positive and negative charges creating a dynamic balance. The strong nuclear force holds atomic nuclei together, but it also has a repulsive component that keeps protons from getting too close. Gravity alone is a monodirectional force, a constant cosmic tug that never pushes back. This singular nature is crucial for the arrow of time. An attractive force naturally encourages clumping. It takes a nearly smooth distribution of matter and draws it into dense clusters like galaxies and stars. This process does not create order out of chaos. Rather, it trades one form of disorder for another, far greater one. When a vast, diffuse cloud of gas collapses under its own gravity to form a star, the gravitational potential energy of the widely separated particles is converted into an immense amount of heat and light. The entropy, the disorder of the universe skyrockets. A newly born star is a fantastic engine for increasing entropy, taking concentrated gravitational energy and radiating it away as disordered light across the cosmos. If gravity could be repulsive, the story would be utterly different. Imagine a universe where masses could push each other apart. Instead of collapsing into stars, gas clouds might simply dissipate into an ever more uniform haze. Or perhaps the universe would oscillate, expanding until repulsive gravity took over, then contracting again in a potentially endless cycle. In such a world, the clear, one-way progression from a smooth beginning to a structured present might not exist. Time could, in theory, be reversible, but our gravity offers no such escape. Its pure attractiveness ensures that once structure begins to form, there is no going back. It helps lock the cosmos into an irreversible path, from simplicity to complexity, and ultimately toward the final equilibrium of heat-death. The ultimate expression of this relentless pull lies in the darkest corners of the cosmos. Even the most extreme distortions of spacetime seem to bow to the universe's one-way street. General relativity, our most successful theory of gravity, presents a tantalizing possibility: wormholes. These are not tunnels through space, but shortcuts through the very fabric of spacetime itself, potentially connecting two distant moments in time as well as location. If such a structure could exist and be stabilized, it could theoretically form a closed time-like curve, a path through the cosmos that loops back onto itself, allowing a traveler to return to their own past. It is a concept that has fueled science fiction for generations. Yet, the universe appears to have built-in safeguards. To hold a wormhole open against the crushing force of gravity, you would need a truly bizarre substance, something physicists call exotic matter. This is not just unusual material, it is matter that possesses negative energy density, effectively generating a form of antigravity to prop the wormhole's throat open. There is no evidence such matter exists or can exist in the quantities required. More fundamentally, most physicists believe that quantum effects, the unpredictable jitter at the smallest scales, would inevitably conspire to destroy the wormhole the moment anyone tried to use it for time travel. The vacuum of space itself would become unstable, unleashing an infinite burst of energy that would slam the door shut. The apparent impossibility of closed time-like curves is a powerful clue that the cosmos actively protects the integrity of cause and effect. It prevents paradoxes like the famous grandfather paradox, where you could travel back and prevent your own birth from ever arising. The universe seems to have a profound allergy to such logical inconsistencies, reinforcing the forward march of time. If even the most dramatic warps in space-time cannot reverse the arrow, perhaps the only place to look for time travel is on a scale so small it defies our perception. This quantum jitter is not just a curiosity, it is a fundamental feature of reality. The 19th clue lies in a principle that trades precision for possibility, the time-energy uncertainty principle. In the quantum world, you cannot simultaneously know both the exact energy of a system and the exact time at which that energy was measured. The more tightly you pin down one, the more the other becomes blurred. This inherent fuzziness has a startling consequence. For vanishingly brief instants, the strict conservation of energy, a cornerstone of classical physics, can be temporarily suspended. Out of the seething vacuum of empty space, particle-antiparticle pairs can spontaneously flicker into existence, borrowing energy from nowhere before annihilating and vanishing back into the void a moment later. These are virtual particles, and their ghostly dance is a direct result of this uncertainty. Could such fleeting events, unshackled from energy conservation, also be unshackled from time's arrow? Could they represent microscopic pockets where time runs backwards? The mathematics suggests that these quantum fluctuations are, on average, symmetric in time. A virtual electron and positron popping into existence and then vanishing looks the same whether the film is run forward or backward. It is a perfectly reversible loop. Yet this potential for reversibility is an illusion when viewed from our larger perspective. These fluctuations are not isolated miracles. They occur within an environment, and any attempt to measure or interact with them, to confirm their brief existence, requires an exchange of energy that inevitably increases the entropy of the surrounding world. The local, reversible dance of the virtual particles is instantly overwhelmed by the global, irreversible tide of increasing disorder. Any tiny reversal is immediately swamped by the forward march of the entire system. This reveals a profound hierarchy. At the smallest scales, time's arrow might flicker, but it is decisively enforced by the larger thermodynamic context in which those scales are embedded. These quantum fluctuations, however, were not always so insignificant. In the first moments of the universe, when all of existence was compressed into an unimaginably small volume, this quantum fuzziness was not a minor effect. It was the dominant force. The entire cosmos was a sea of such fluctuations, a realm where the very concepts of before and after may have been blurred. This primordial state holds the key to understanding how a universe that permits momentary reversals at the quantum level could still give rise to the stubborn, one-way arrow of time we experience today. That primordial quantum fuzziness, once the dominant reality, needed a mechanism to be stretched into the vast cosmic structures we see today. This brings us to the 20th clue, a theory that addresses the very first moments of everything: cosmic inflation. Picture the universe in its first sliver of a second, a realm of unimaginable energy where quantum fluctuations were not minor events but the very texture of spacetime. The theory of inflation proposes that this infant universe underwent a fantastically brief but explosive period of exponential expansion. In a time span far shorter than the blink of an eye, a region smaller than a single subatomic particle was stretched to a size larger than our entire observable universe today. This was not the steady, stately expansion we see now, but a violent, hyper-fast stretching of the fabric of reality itself. This process is profoundly irreversible. Think of inflating a balloon with an impossibly powerful single burst of air. Once inflated, the balloon cannot spontaneously shrink back to its original tiny size. Inflation locked the universe into its expanded state, setting the stage for the billions of years of slower expansion that followed. But its role in time's arrow is even more critical. That initial state of incredibly low entropy, the wound-up spring of the cosmos, was effectively set and sealed by this inflationary burst. The rapid stretching smoothed the universe to an incredible degree, creating the vast, uniform sea of energy we detect in the cosmic microwave background. Yet it also took those tiny, random quantum fluctuations and magnified them, stretching their imprints across the entire sky. These microscopic seeds of imperfection, born from quantum uncertainty, became the gravitational seeds for every galaxy, star, and planet. Inflation, therefore, is the ultimate cosmic amplifier. It took the potential for reversibility at the quantum scale and blew it up to a cosmic scale where the thermodynamic arrow of time became inescapable. It established the initial conditions from which all other arrows of time inevitably flow. With the stage so decisively set, we are left to ponder the final, most encompassing clue, one that asks what all these arrows truly mean for the nature of reality itself. This stubborn one-way street of time is the very foundation of meaning in our lives. If time were truly reversible, if cause and effect could dance in either direction, our most cherished concepts would dissolve into absurdity. What would free will mean if your future choices could rewrite your past decisions? What would responsibility be if a crime could be committed after its own punishment? The irreversible flow of time carves a single, unchangeable path from the past, giving our present actions weight and our future possibilities genuine consequence. It creates a stage where progress is real, where learning from history is possible, and where a promise made today cannot be unmade tomorrow. This is not a philosophical abstraction. It is a direct consequence of the physical laws we have traced, from the decaying Kaon to the expanding universe. Our linear experience of life, our sense of a narrative with a beginning, middle, and end, is not an illusion separate from the physical world. It is the human-scale expression of the cosmos' deepest, most fundamental bias. The universe did not accidentally produce conscious beings who mistakenly perceive time's flow. Instead, a universe with a strong arrow of time is the only kind of universe complex enough to give rise to beings who can reflect upon it. The increase of entropy, the collapse of quantum waves, the formation of galaxies, and the formation of a memory are all threads of the same irreversible tapestry. Having journeyed through these 21 clues, from the quantum vacuum to the heat death of the cosmos, a unified picture emerges. Time's arrow is not a single mystery but a symphony of constraints, each clue reinforcing the others. The low entropy beginning set the stage, thermodynamics provides the engine, quantum measurement creates definite reality, and cosmic expansion furnishes the arena. This interlocking system suggests that our universe is profoundly historical. Its present state is a unique product of a specific, irreversible sequence of events. The arrow of time is the universe's way of having a story, and we, in our brief moment of consciousness, are not just reading that story, we are living it. This interconnected web of evidence points toward a profound conclusion about our place in the cosmos. Each of these 21 clues, from the cooling of your coffee to the evaporation of a black hole, is not a separate mystery. They are different facets of a single, monumental truth. The arrow of time is an emergent property, a symphony played by countless instruments, all tuned to the same fundamental key. That key was struck in the first moment of the Big Bang, the ultimate low-entropy starting gun. The fundamental equations of physics, when considered in a sterile, abstract vacuum, may be perfectly reversible. They do not care if time runs forward or backward, but our universe is not an abstract equation. It is a specific, historical entity with a unique and powerful initial condition. This is the crucial distinction. The laws provide the rules of the game, but the initial state provides the playing field, and it is a field with a steep, one-way slope. Everything that has unfolded since, the formation of every star, the evolution of every life form, the very process of you forming a thought, is a consequence of the universe sliding down that slope toward greater disorder. Your memory does not work in reverse because your brain is a physical system recording information, a process that burns energy and increases entropy. The cup shatters and does not reassemble because that path leads to a more probable, more disordered state. The universe expands because that ever-growing arena provides the room for entropy to endlessly increase. These are not isolated phenomena. They are dominoes in a chain reaction that began 13.8 billion years ago. This synthesis reveals that our linear experience of life is not a quaint human illusion. It is the direct, conscious experience of the universe's most fundamental and irreversible narrative. We are not outside observers of time's arrow, we are manifestations of it. Our very existence as thinking, remembering beings is a product of a cosmos that has a past, a present, and a future. In a universe without this arrow, without this clear distinction between cause and effect, complexity like planets, life, and minds could never arise. The arrow of time is the universe's way of having a story, and we are living paragraphs in that grand cosmic tale. Our journey across the scales of existence reveals a universe unified by a single, powerful narrative. From the quantum dance of a single particle to the relentless expansion of the cosmos, every clue points to an inescapable conclusion. Time's one-way direction is the ultimate feature, not a bug. It is the necessary condition for everything we hold meaningful. Without this irreversible flow, there could be no learning, no growth, no memory, and no possibility for choice. The very concepts of cause and effect, of regret and hope, rely entirely on the fact that the past is fixed and the future is open. This is why a melting ice cube never refreezes spontaneously in your glass, and why you can recall a childhood birthday but not next year's holiday. These mundane moments are local echoes of the grandest law, the universe's unwavering march from a unique beginning toward an uncertain future. The arrow of time is the canvas upon which the story of reality is painted, and our consciousness is a brushstroke in that masterpiece. If this exploration of time's deepest secrets has changed your perspective, share your thoughts in the comments below. Consider subscribing for more voyages to the edge of understanding, because the universe is always stranger than we can suppose, and the enigma of time lies at the very heart of that wonder.